Hello again. We're now going to look at the last lecture for this section, and it's going to be about bond properties, order length, and dissociation enthalpy. So, bond properties, order length, and dissociation enthalpy. The goal is to understand the properties of covalent bonds, bond order, bond length, and bond dissociation enthalpy, and their influence on molecular structure and properties. So, we're going to look first at the bond property of bond order. Bond order is basically the type of bond based on the number of shared electrons. A single bond is a bond order of 1. A double bond is a bond order of 2. A triple bond is a bond order of 3. So in carbon dioxide, you have 2 bonds. This is a double bond, a bond order of 2, and this is a double bond, a bond order of 2. So, well, let's look at one more example here. We looked at 3 different molecules when we were looking at the previous section for molecular polarity. So let's take a look again at some other molecules. So I call this molecule formaldehyde. So what is the bond order here between the carbon and the oxygen? The bond order is 2. How about here between the carbon and the hydrogen? The bond order is 1. And how about here? The bond order is 1. Now, what about for hydrogen cyanide? What are the bond orders? Well, here, the bond order is 1. And next to it, the bond order is 3. So most bond orders are pretty easy to tell. You just look at the molecule and you say, well, is it a single bond? Bond order 1, and so forth and so on. Let's take a look here for bond order for resonance structures. So for the carbonate ion, there are 3 resonance structures. One can have the double bond on this oxygen, one can have the double bond on this oxygen, and the third can have the double bond on the third oxygen. So really, each of these molecules represents the molecule of carbonate, or I should say molecule, the polyatomic ion of carbonate. And we have to understand that this molecule is not correct because if you look at the bond order, we've got a 2, a 1, and a 1, and the 2 should be much shorter than the 1s. But in fact, in this molecule, it's found that all of the bond orders are the same, and they're in between a 1 and a 2. They're not as long as a 1, nor are they as short as a 2. So how do we explain this? Well, to get a bond order where the resonance structures are all equivalent, you simply look at all 3 resonance structures in this case, and you look at the bond that is the same in each one. So remember, these 3 molecules are not 3 molecules, they're the same molecule drawn 3 different ways. So what is the real bond order right here between this carbon and this oxygen going down to the left? Well, it's not a 1, it's not a 2, and it's not a 1. But it is an average of a 1, a 2, and a 1. So how do you get the average? Well, 1 plus 2 plus 1 is 4. We have 3 structures. So the bond order for this bond, number 2, is 4/3. So it's the total number of bonds and all the resonance structures divided by the total structures for that bond. So notice I said for the oxygen going down to the left. This oxygen, the ones I'm pointing at now, they are the same oxygen. There's not 3 oxygens there. They are the same oxygen. So what is the bond order to that oxygen? Well, we have a single, and a double. That's 4 bonds divided by 3 structures. It's also a 1 1/3 bond. So 1 1/3 bond is a little bit shorter than a single bond, but longer than a double. And we find that all of these are the same. Now, the way the book does it is they just look at one of these and they say, well, since these are all equivalent, we just average them. And that's not the way you do it. And let me show you why that's the case. So let's look at bond order for non-equivalent resonance structures. So remember, the cyanate ion has two good resonance structures due to formal charges. This one has a formal charge on the oxygen of -1. This one has a formal charge on the nitrogen of -1. The rest are zeros. So the electron neutrality principle works out pretty well because most formal charges are zero on these guys. So if we followed the book's idea, they'd say, well, okay, that's a single, that's a triple. We have two bonds there, or I should say we have four bonds total, and one bond to this side, one bond to that side. So it's 4 divided by 2. The bond order is 2. And then they'd look at this and say, well, you have a 2 and a 2. And so 2 and 2 is 4 divided by 2 types of bonds here. And that's 4 divided by 2. So you got a bond order of 2. Wrong. Absolutely wrong. Here, this oxygen is this oxygen. So we have to look at the bond order between carbon and oxygen here, where I'm tapping, and the bond order between this carbon and oxygen here, where I'm tapping. Here we've got a single bond and a double. That adds up to 3. 2 structures. 3 divided by 2 means the bond order for carbon-oxygen is actually 1.5. A little bit longer than a double, a little bit shorter than a single. Remember, singles are longer, doubles are shorter. Okay, what about the carbon-nitrogen bond? What is the bond order? Well, we have to average these two. This is a 2, this is a 3. That's 5 bonds over 2 structures. 5 bonds over 2 structures is 5/2. So this is a 2.5 bond. So naturally, we would expect the carbon-nitrogen to be a little closer than the carbon-oxygen because its bond order is greater. Okay. Next bond property we're going to look at is bond length. So I call that BL. This is the distance between nuclei of bonding atoms. And we can kind of estimate which bond lengths are shorter and longer just by remembering the radii. Now, for the same 2 atoms, the higher bond order is the shorter length. So when I say the 2 same atoms, they could be a carbon and a carbon, carbon and a nitrogen, carbon and an oxygen, just as long as you're comparing the 2 atoms that are the same. So take a look here. So I'm looking at only carbon-carbon bonds. So there's a single, a double, and a triple. And when we talk about the length, the single is longer than the double, is longer than the triple. The triple is the shortest because there's more electrons that are pulling the nuclei together, making the distance between the nuclei smaller. Okay, and here I have another example where you have 2 of the same atoms, only it's this time instead of carbon-carbon, you've got carbon-nitrogen. A carbon-nitrogen should be longer than a carbon double bond nitrogen, should be longer than a carbon triple bond nitrogen. Again, the triple bond is going to be the shorter of these 3. It's hard, though, to compare a carbon triple bond nitrogen to a carbon triple bond carbon. We could make the guess, though, here for the carbon-carbon versus carbon-nitrogen. We know that the atom size gets smaller as you go across the period. So that means a nitrogen should be smaller than a carbon. So therefore, when you look at the bond length between a carbon and a nitrogen, it should be a little shorter than the carbon-carbon. Okay, now you aren't expected to memorize any any bond lengths. So we're not going to worry about that. Okay, let's see now. What I have here is the book. Remember, we predicted that a carbon-nitrogen bond length should be a little bit shorter because nitrogens are a little bit smaller. So here's a carbon-carbon bond length, 154. And here's a carbon-nitrogen bond length, 147. A little bit shorter because the nitrogen atom is a little bit smaller. Okay, moving along here. Next, we have bond properties. Bond dissociation enthalpy. A lot of people use the letter D to represent this property for dissociation. It's the amount of energy to homolytically break a covalent bond in the gas phase. So this is in the gas phase, and here you've broken the bond, Each atom gets one electron. That's called a homolytic breakage or cleavage. Here you got two electrons also bonding the two hydrogens together. And when we break this bond, both electrons end up on one atom and none on the other. This is a heterolytic cleavage. So we're talking about this one up here, a homolytic cleavage, not the heterolytic cleavage. It's a different amount of energy for the heterolytic cleavage. So the deal here is that when we look at the bond association energy, which is endothermic, you have to put energy in to break the bond. Here's the deal. You have to put less energy in to break a single bond than a double bond, and more energy in to break a triple versus a double. And you're not supposed to memorize these numbers. These are just here so that you can validate the idea that triples are harder to break than doubles. Doubles are harder to break than singles. Okay. Now, we can actually use bond dissociation enthalpy to calculate the enthalpy of a reaction. So the enthalpy of a reaction is equal to the sum of the bond dissociation energies of the bonds broken. So here, this is at the beginning because when we're breaking bonds, it's endothermic, right? Now, when bonds are formed, it's the opposite. It's not endothermic, it's exothermic. So we have to have a negative here to turn all these bond association energies into negative values because energy is released when you reform those bonds. So we can actually use this formula to calculate the enthalpy of reaction. So let me show you how that's done. So this takes a little bit of time. So we're only going to do one example problem. And let's take a look at this. Acetone, a common industrial solvent, can be converted to 2-propanol rubbing alcohol by hydrogenation. Calculate the enthalpy change for this reaction using bond enthalpies. So here's the reaction. So I'm going to write it out, but I'm going to write it out a little bit differently. This CH3, we know this carbon is supposed to have 4 bonds, so this is what the CH3 really looks like. I'm going to go ahead and put the lone pairs on the oxygen. They're missing. So there's acetone. There's hydrogen. And we're going to make 2-propanol. So here's the structure of 2-propanol. If you look to make sure that it's balanced, you'll notice 1, 2, 3 carbons, 1, 2, 3 carbons, 1 oxygen, 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. So it's balanced. So let's take a look at how we use the formula that the enthalpy of the reaction is the sum of the enthalpies for bond breaking, because we had to put energy in, so that's plus, minus enthalpy change for bonds formed. So when the bonds form, it releases energy, which is a negative. Okay, so for this, we have to look at all the bonds that are going to break. And the idea is that we break every single bond here, and then we just reassemble it and make all of these bonds. So let's take a look at the bonds that we're going to break. We're going to break a carbon-hydrogen bond here, a carbon-hydrogen bond here, a carbon-hydrogen bond here. In fact, we're going to break 1, 2, 3, 4, 5, 6. So we're going to break 6 carbon-hydrogen bonds. And we need a change in enthalpy for that. And so what we really should be writing here is 6 times that change in enthalpy for a carbon-hydrogen bond. What other bonds are we breaking? Well, we're going to have to break a carbon-carbon bond here and a carbon-carbon bond here. So we're going to add 2 carbon-carbon single bonds. We also have to break this carbon-oxygen double bond. So we're going to have 1 carbon, oxygen, double bond. So those are all the bonds that we have to break, but then there's one more. There's this also. So +1 hydrogen, hydrogen, single bond. So we're going to sum these, and actually we don't need this anymore. We can just put a bracket around that. And now let's look at all the bonds we form. 1, 2, 3, 4, 5, 6, 6 carbon hydrogen bonds. Oh, I forgot my delta H's in here. So let me rewrite this so I got my delta H's in there. 6 delta H carbon hydrogen +2 delta H carbon carbon +1 delta H carbon oxygen +1 delta H hydrogen hydrogen -6 delta H carbon hydrogen, because there's 6 of those. 1, 2, 3, 4, 5, 6. When you're counting up the bonds you're breaking and making, it's a good idea to cross them out. So there's 1, 2, 3, 4, 5, 6. So those are the 6 we've made so far. Since I crossed that one out, I'm going to write that down next. So +1, change in enthalpy of a carbon hydrogen bond, +1 carbon oxygen single bond, and then +1 carbon oxygen single bond. Oh, excuse me, oxygen hydrogen single bond. Okay, so we need to look up the enthalpy change, or the bond association energy, for each of these types of bonds. Now, you can tell here that since we have 6 carbon hydrogen bonds and 6 carbon hydrogen bonds, this minus this is going to be a push and be 0. So we don't need to look those up. Now look at this. We have a hydrogen-hydrogen bond. Do we have one over here? Nope. We have a carbon-carbon bond. Do we have any over here? Nope. Carbon-carbon double bond. Do we have any over here? Nope. So we need to look up all the rest of these. So here's what they're going to be. So let's look at a carbon-carbon single bond. Now, I'll give you this table. You don't need to memorize it. We want to look at the energy to break a carbon-carbon single bond. So here's the energy, 346 kilojoules per mole. So this is the table you look at. I'm going to put that off to the side, and I'm going to write the values down. So a carbon-carbon single bond is 346 kilojoules per mole. I'm going to leave the per mole off. +1 times, so carbon-oxygen double bond is 745 kilojoules. And here, a hydrogen-hydrogen single bond is 436 kilojoules. So that's the end of the top bracket here, the beginning bracket, minus, whoops, we have a carbon-hydrogen bond, one of those. That's that one right there. So that's going to be 413 plus, because remember, this sum means plus. We sum all these, but then after you sum them, you subtract them from those. So now we have a carbon-oxygen single bond, which is 358. And then finally, we have a oxygen-hydrogen single bond. And that's going to be 436. Excuse me, 463. Okay, so I'm going to bring out my trusty calculator, but I'm going to estimate first. I think everyone could agree that if we added these two numbers together, we'd get close to 1,200. And then 2 times this is close to 700. So this is close to 1,900. 1,200 plus 700 is close to 1,900, a little less. Here, 413. Well, actually, let's add these two numbers together, 358 and 463. That's going to be close to 800, a little more than that. And then 800 plus 413 puts us at I don't know, 1250. So if this is 1250 and 1900, the difference should be around 650 kilojoules. And it's going to be a positive value because this is bigger than that sum. So let's add these up together. 2 times 346 plus 745 plus 436 is equal to 1,874 kilojoules minus, so over here, we're going to have 413 plus 358 plus 463, which is 1,234 kilojoules. Now here, this times this is over 1,000. And we get 3 zig figs, so this number is only going to be good to there. This number, however, is good to here. When we do the subtraction here, we get 640 kilojoules. Okay, and this is only good to the tens, so there's our answer. So what this means is that to make this actually happen, we have to put energy in to make it happen. It doesn't happen by itself. So this whole reaction is endothermic because this value here is positive. And that's how you get the enthalpy of a reaction using bond dissociation energies. Whoops, the R goes there. All right, thank you for listening. Appreciate it.